So topic 2.14 kind of starts to end our studies of logarithms. We have one more topic, obviously, but at the end of each time we've studied a type of function, we've also done regressions and looked at context and data for that type of function. So that's what this lesson, this topic is going to focus over. If you see right here, the first table you have is the average salary for a church pastor across the U.S. and seeing that the average salary increases as the size of the church increases. Okay, we have this right here. We can clearly see there's a pattern in the data, but the models we have previously used are not appropriate yet for this data. The growth above displays a large rate of change initially. Look, big jump, big jump, big jump, big jump. But then as the church size increases, we see the rate of change gradually decrease. The bump up each time gets less and less. The data above appears to be logarithmic. So what we're saying here is that we see this sort of trend where we're increasing a lot at first, and then the rate at which we are increasing decreases. So that is increasing at a decreasing rate, which is what we know means that this graph is concave down. It is increasing and concave down, increasing at a decreasing rate, because the church pastor gets a lot of salary bumps right at first, and then it slows down as the church keeps growing. Just as we have seen with other types of functions, many real-world scenarios follow a logarithmic pattern. Outside of this example above, logarithmic patterns are found in the way we measure earthquakes, sounds, acidity, and other context. As a result, we need to make sure we know how to model this data using technology so we can actually take experimental data and do something with it. There are obviously many types of logarithmic function models we can use because we have all of the bases that will change. There are two important logarithmic model equations that we're going to need to know. The first one is y equal to a plus b times natural log of x. The second one is a plus b times the common logarithm of x, where a and b are going to be some constants and b cannot be 0 because then you'd be multiplying the logarithm by 0. So we have this first one that I've highlighted in pink. What's the base of this pink logarithm? E. What's the base of the blue one? You can also see this one written with other bases. So this could be log base something to the x power, of x. Wow, said that wrong. So either way, the log base will just change the logarithm that we're using. Okay? The selected values of some logarithmic function L are given in this table, where L is written in this form. We're going to highlight this one in the same color you highlighted my pink equation in, because look, it is telling us the type of function it wants us to write. That is the way your answers should look because it's asking for logarithms written in that pattern. The first part, and we've seen this already in a different context, it says, use the given data in the table to write two equations that can be used to find the values for constants a and b in the expression for L of x. We did this with exponentials, but we were mediocre at doing it. So let's hear it again and see if we can fill this in. If we're trying to find a and b, you don't plug anything in for a and b. You plug in the data from your table. Your table is labeled as x and the output L of x. You're going to plug those numbers in on the input and on the output, meaning this first equation we're writing should be a plus b times the natural log of 2 equal to 3. The input goes inside the logarithm. The output goes on the equal sign by itself. Do you see where I'm getting the 2 and the 3 from? So what would my second equation look like? Very good. Here's a note that I'm going to start switching to, and I wanted to write it in print at first. When I'm working with natural logs, and it happens every year in my AP classes and in my dual credit classes, that somebody still thinks that that is the letter IN. That is LN for natural log. So from here on out, I'm going to be writing my natural logs in cursive so that it looks significantly different from print. I just didn't want to start in cursive in case some of us skipped cursive in kindergarten and can't read that. It happens. I get it. We didn't teach you guys. We need to work on that. Does everybody know how to draw their signature, by the way?
Yeah. Draw
like write your signature in cursive?
Yeah.
Ooh, I'm seeing, okay, I'm hearing no. we'll have a little mini lesson soon on cursive. Got you. Part B says, without the use of a calculator, find the values of A and B. If we look at what we've created up here, these two equations are a system of equations. Two equations, 1, 2, two unknown values, A and B. If you have two equations and two unknowns, you can solve. So let's have a little Algebra 1 moment, and let's solve this system of equations by hand using elimination, which means we're going to keep the first one exactly the same. A times B, A plus B times the natural log of 2 equal to 3. And I'm going to change every sign of the second equation, meaning this is now negative A minus B times the natural log of 5 equal to negative 7. When you learned how to solve systems by elimination, forever ago, you needed to line them up to where the letters are on top of each other and they're opposite signs. If I were to add these two equations together like an elementary school style problem, if you have positive A and negative A, what's going to happen? They cancel out. But then I have B times the natural log of 2 minus B times the natural log of 5 equal to negative 4. What do you notice right now that the two terms on the left side of my equation both have on them? Ooh, B, but yes, they both have a B. So I'm going to factor out the B so that I'm just left with natural log of 2 minus the natural log of 5 on the insides. Whoa, spidey senses should be going off. When you're subtracting logarithms, what can you do to condense them? I heard it. Divide. Very good. So that means we have B times the natural log of 2 divided by 5. That's what's going to be equal to negative 4. Now, we've kind of lost the plot here. What are we trying to solve for? A and B. Can I get B by itself? Yeah, if I take that natural log and I divide it away, which means B is going to be equal to negative 4 divided by the natural log of 2/5. Last class you learned that this is a nice place to stop. This is called an exact answer. After we got the exact answer, what did you do to finish answering my questions? Plug it in. Yes, we're going to get a decimal approximation. So with your calculator right now, I want you to press negative 4 divided by natural log of 2/5. And I need everybody to do this because we're going to do a step after this that you've probably never done before. In fact, let me show you on the big calculator on my screen. Fabulous. So we're going to approximate that on our paper to be 4.3654. Amazing. But in this class, I've told you don't ever round to the very end. If this problem had a part 3 and it was asking us to do something with this value, we want to make sure we're using the entire thing, the exact answer. So to save ourselves some time in our calculator, we're going to press this button right here that says STO with a little arrow. That is the store button. What you're going to do is you're going to press that once, and it says on your screen, take the answer you got, this, and I'm going to store it, and you need to tell a letter. What letter did we just solve for? B. So I'm going to press alpha and then apps, which has the letter B. Your calculator screen now says, I'm going to take the answer, I'm going to store it as B. You press yes, which means enter. You have now stored this entire value B on the B button. So if I press B and press enter, it's going to return that value for me. So if you were using this in a part 3 or a part 4, you want to use the whole number, not a rounded number. We round at the very end. Okay, fabulous. So now for notation for myself, whenever I do this in my calculator, I always tell myself that I stored it as the letter B. That way in my head, I know, thank you. That it's stored as B. Okay, we've done half this problem. What else does it ask us to find though? A. So now I'm going to go back to one of the original equations. I'm going to say A plus B. Oh, look, that B is now the stored value B times the natural log of 2. Can I solve for little a? Yeah, how do I get that big B natural log of 2 to the other side? Subtract it. So I'm going to do a equal to 3 minus the stored value b times the natural log of 2. That really doesn't look like the word natural log. Let me try that again. And in your calculator, to calculate the value of a, we're not using the rounded number. We are literally going to type 3 minus the stored value b times the natural log of 2. So now we found this value of a in our calculator, and it is approximately, if we were writing this down on our paper, 0.0259. But we want to store this letter. What letter did we just find? A. So I'm going to press the store button and alpha math to get the A button. It has now stored this number as big A. So if there was a part 3, you could use the buttons A and B on your calculator to use those numbers instead of the rounded number. Yes? So we did technically answer the questions here. You're like, we did a lot of work in this tiny little space. I know, so sorry. Here's B. Here's A. Those are the values of A and B. So what happens, though, if we don't just have 2 pieces of data? So in the first problem on the other page, I only gave you 2 coordinates. That's all you need to do a regression by hand. But what if you have all of this data that you want to take into account to really make a good regression for your information? Instead of doing this by hand, you can also do these regressions to find the values of A and B in the calculator. So we are going to go to stat edit, but before we go, because I know some of you are going to get ahead of me, let me just read part A to you. It says, use the regression capabilities of your calculator to find a logarithmic function model for the data above of the form A plus B times the natural log of the input value P, where P is the church size and S is the average pastor salary in thousands of dollars. The option on your calculator that gives you the regression of a natural log when you go to stat calculate is option 9. It says LN reg. That is important for you to know because your calculator will only do a natural logarithm regression. It will not do a common logarithm regression. It will not do a logarithm with base 5 regression. So if you get a problem where it's natural log, bonus, yay, we get to use our calculator. Otherwise, we have to do it by hand. But let's do this one in the calculator. Do y'all need me to walk through the steps, or do we think we got it? That is a 9, yes. Let's already start. So go ahead with your calculator. I want you to go to stat edit. I want you to put in all of that data. Yes, every point is important. We're wanting to make our data accurate. Okay, those of you who have finished, let's check our work. Those of you who are still typing, keep typing away. We should get S of P equal to negative 91.5420 plus 29.9088 times the natural log of P. It's salary for people. Well, the input is church size, so I'm assuming that stands for population. P for population and S for salary.
That's a lot of salaries for pastors instead. Average salaries. You tell her.
Okay, for B, this is why storing this in Y1 is very important. It says using the model found in part A. Model is an equation. So using the equation found in part A, what is the predicted annual salary in thousands of dollars for a pastor whose church size is 500 people? Oh, look, P for people, which means we are trying to find S of 500. I don't want to type these numbers in myself because they're rounded. We want to let the calculator use the entire number that we got, which is why we want to do the Y1 of 500 in your home screen of your calculator. Otherwise, you're giving me a rounded number that's going to be different and wrong. I want you to use the entire number that we have stored in the calculator.
What about the log of p?
The natural log, it's here.
Do we put it in there though?
What do you mean?
Like before the 500? Do we put
One.
No, because the natural log of p is a part of your equation that the calculator knows, because we told it to use that pattern. We should get, if you guys done this in a calculator, we should get 94.3295 dollars in thousands. In this problem, we plugged in 500. Why? Why did we choose to plug in 500? The church size is 500 people. That was my input value. If you were somehow given the salary and it says, what is the population size if the salary is 500,000? Instead of plugging it in, what you would do, because it's a calculator question, so here, if given an output and we're solving for the input, instead of solving it with the y1 parentheses, you're going to go to y1 and you're going to make sure that your equation is typed in. And it should be, because your calculator stored it there. In y2, you're going to put that output value. And if you have an equation in y1 and an equation in y2, what are you looking for? Where they intersect, so that you can find the input value, the x value. Okay, so if you're given an input, plug it in. If you're given an output, set them equal to each other on your calculator and find the intersection point. We've done this. We did this last class. I know we know how to do it. We're not showing an example. We're going to go to example 3, though. The most common and preferred method to measure sound intensity levels is in decibels. Y'all have heard of this before, right? Decibels. Fun fact, did you know that deci refers to the fact that the level of sound is found by multiplying by 10? Deci is 10. Deca, 10, right? Bell refers to the man who created this, Alexander Graham Bell. He's the inventor of the telephone and the person who decibels are named after. So kind of cool, we named it after a person. Decibel, Alexander Graham Bell. Anyways, that's just a fun fact. Decibel, yeah. Decibel. The sound intensity level, this is beta. This is a Greek letter beta. The sound intensity level beta in decibels of a sound having an intensity I in watts measured per meter squared is modeled by this function. Is this a natural or common logarithm function? Does our calculator do common logarithm regressions? No, so our spidey senses should tell us we're going to practice this thing by hand one more time. We got the calculator, no big deal. Okay, this noise, wow, what? The sounds of a noisy traffic has the intensity of 1 times 10 to the negative 5 watts per meter squared and corresponds to 70 decibels. Quick question for all my science friends. What is this number written as a decimal?
No, 0, 0, 0. There's 4 zeros.
Yeah, it's 4 zeros.
0.00001. Why? Scientific notation tells me to move the decimal point 5 times to the left. From behind the 1, I move it 5 times, so that's the number 0.00001. A loud concert has an intensity of 1 and corresponds to 120 decibels. Use the given equation, given data to write 2 equations that can be used to find the values for constants a and b in the expression for beta of I. We would plug them in. Remember, we're not plugging in an a and b, we're finding a and b. A plus b times the logarithm of 0.00001 is equal to what? 70. Right.
You can still put it in scientific notation, correct?
Yes.
Do these calculators?
Yes, but I prefer the decimal. A loud concert has intensity of 1, so this is a plus b times the logarithm of 1 and corresponds to 120 decibels. Because our output is decibels when our input is intensity. So I put the intensity numbers inside and the decibels on the outside. But let's practice the same steps. Those of you who are recognizing some of these numbers, I know I'm going to do this the long way, but I want us to see another example of the solving the system. And look, I gave you a little bit more room this time. To solve this system by hand, and remember, we have to do by hand because it is not natural log, we will do this. We will say a plus b times the logarithm of 0.00001 equal to 70. And then exactly the opposites. Negative a minus b times the log of 1 equal to negative 120. We set up a system for ourselves to solve by elimination. So I add the equations together. A and negative a cancel each other out. I have b times the log of 0.00001 minus b times the log of 1 equal to negative 50. What do both of those logarithms have in front of them? B. So we're going to factor out the b, and we have log of 0.00001 minus the log of 1. When you're subtracting logarithms, what can you do with the numbers? Divide. This is b times the log of 0.00001. I don't know why I put that parentheses there. Divided by 1. What is any number divided by 1? 1. Wait, what? The same number. We're here. So instead of writing that as a fraction and making it look super complicated, let's just do this once. Because 0.00001 divided by 1 is still that number. Easy. How do I get b by itself? Yeah, that's how I get it by itself. How do I move it to the other side? Divide is currently multiplied by b, so to do the inverse, I would divide. B is equal to negative 50 divided by the logarithm of 0.00001. Whew. What did we do before for this? Plug it in. Let's go for it. In your calculator, negative 50 divided by the logarithm of 0.00001. Of negative numbers. It's 10. Ah. Do we need to store that number? No. We can type the number 10. Well, you can. You don't have to. You can store it as b if you want. Go for it. But since it's a number we are not rounding, you don't have to store it. We can then use that number to find a. So we would have a plus b times, not b, sorry, 10 times the log of 0.00001 is equal to 70, which means a is 70 minus 10 times the logarithm of 0.00001. And when you throw that in a calculator, what do you get? Yes.
3,500.
Yes, we get 120. So we found the value of B and we found the value of A.
Oh.
10 is B, 120 is A. You have a question mark face. Can you ask your question?
The second one though, it's 20 as the answer, but A is also 120?
Uh-huh.
Okay.
Let her cook, let her cook. Part C says the human eardrum can burst when sounds reach an intensity level of 1 times 10 to the 4th. Science friends, what number is that?
There's 4 zeros behind it.
There's 4 zeros behind it. 10,000. So when we reach an intensity level of 10,000 watts per meter squared, according to the model found above, what is the predicted number of decibels required to burst a human eardrum? Giving me 10,000 watts per meter squared, did they give me the input or the output? Input. They gave me that the intensity of this sound is 10,000. which means we are going to plug it into our formula. What formula, Miss Quigley? Great question. It's beta. Beta of 10,000. And we didn't put anything in our calculator stored, so we are going to do this one by hand, and that's fine because these are cute numbers. Would be A plus B times the log of that value, 10,000. Because remember, this was A plus B times the log of the input. And that's all numbers. So what in your calculator is 120 plus 10 times the log of 10,000?
160.
So if you burst your eardrums, you probably listen to your music way too loud. This is about the decibels you guys listen to your music in your headphones. Ooh, that's fine. No. Don't burst your eardrums, friends. I've done it. It's not fun.